All right, in this section, we're going to be looking at acceptance sampling. Now, acceptance sampling is a technique of pulling a certain number of items from a larger set and being able to make an accurate assessment about the quality of that entire set. This is, in fact, a very common technique in factories to assure high-quality products, where they're pulling a certain number of them off the production line and then using them to make an assessment on the overall quality of the larger set. So the goal here is balancing two different criteria. So one, I want to correctly reject faulty merchandise. You don't want faulty merchandise going out. That really ruins your reputation as a provider. It's very expensive to pull all of that, provide new ones, ship them there. And especially, for example, if you're looking at food, then you have to have recalls of food, and that really damages the overall perception of the quality of the merchandise that you're selling. However, we also want to be able to do this with a minimum number of samplings. Each time I'm pulling a sample and testing it, keep in mind that is costing me time and money. So the problem we're going to look at number 18 would be very similar to the type of statistical problem you would have if you were working in a factory and they want to set up the acceptance sampling protocol for being able to correctly reject batches of product that are sufficiently faulty that you would not want them going out, but they of course want to be able to do this with the minimum number of samples necessary to accurately catch these flawed sets. So here we have 810 airport baggage scales. We know ahead of time that 102 of them are defective scales, because again, this is a situation where we're trying to establish, make a recommendation, for example, to the factory production as to what level of sampling they need to be doing. We want to know if we pull 4 of those scales and test them, what is the probability that the entire batch is going to be accepted? Now, if the entire batch is accepted, this is a problem. 102 scales out of 810 being flawed, that's roughly 1/8 of your product. You do not want to be shipping out materials when you've got a 1/8 flaw rate in it. So let's take a look at this problem. The first question to ask is this problem independent or dependent? Well, if you look at this, you notice that they're going along the production line, so we're pulling off one at a time, which means that we would not be doing replacements, so this is going to be dependent. Now, the next thing we need to think about is what probability are we solving for? Now, we're going to have to think our way through this carefully. The answer is not the obvious one. If any one of the 4 samples is defective, we reject the whole batch. So we don't need to have all 4 be defective. We only need to have one of the 4 be defective. So we're not solving for the probability of selecting a defective scale on any one trial, but instead the probability of not getting a defective one for all 4 trials. So we've established ahead of time that with 102 defective scales in this batch, the batch should be marked as defective. It should not be accepted. So if all 4 of our samples pull a non-defective baggage scale, then we would incorrectly assume that the entire batch is good and send it on its way. So what we're looking at here is we can sample the probability any one of these 4 being defective would be enough to reject the entire batch together. Okay, so if we're putting this into our statistical formula, we're going to have the probability of non-defective for the first batch, probability of non-defective for the second batch, given that the first batch, we already pulled 1, and then non-defective for the third sample, given that we've already sampled previously 2 others, and so forth for the 4th probability. So here is how it's written out in our probability formula. Now we need to solve for these probabilities. So if we're looking at this, keep in mind, if we're solving for that they're not defective. So we know 102 are defective. So to get the total number of non-defective airport baggage scales, we would take 810 and subtract 102. Okay, that would give us our number of non-defective, right? So that's going to give us 708. We're going to divide that by 810 because we know we're going for our first sampling, we've got 708 non-defective baggage scales in this set of 810. So we solve that through and we get 0.8740747. And notice I'm carrying these out quite a ways. I like to round only at the end. So as you're in the problem, you want to maintain the full numbers as you work your way through and round only at the end. If you're rounding at each stage, you actually can throw your answer off. Okay, so Now, notice when I go to do my next one, just as we were looking at with the dependent probability, that means that if we removed a scale and it is not defective, this alters both the total number of scales available for the next sample and the number of non-defective scales available. So that means we've now gone to 707 non-defective baggage scales that are in the set, and now we have 809 total baggage scales in the set. So that gives us a probability for our second round as 0.739182. Okay, now complete the last two probabilities on your own, and pause the video while you do that when you've got those solved following the pattern we've just looked at here. Then move on to the next slide to check the answer. Okay, so these are what you should have come out with for your 4 probabilities. So we've got 4 different samplings, 4 different events. Here's our probabilities for each of them. And when we reorganize these into the multiplication formula, we get, notice I had to move the formula just a little bit so these would line up evenly. So here we can see again, this is the same stuff we had listed before, only I've taken it and put it going across so that we can add in our multiplication symbols appropriately. And we get for our final answer with the rounding rule of 0.583. So when we come back, our probability of our probability that the entire batch will be accepted is 0.583. Okay? So we want to ask ourselves, is this approach likely to correctly reject the entire batch? Why or why not? Well, it's not likely because it's little better than chance. So chance would be a probability of 0.50. So that's not going to be good. We want to have a higher, very low likelihood of accepting the batch because the problem is that the batch itself is flawed. So when you're looking at your accepted sampling types of problems, notice that once you get going on it, your rules are going to be the same in terms of your formula, but you need to step back and think carefully about what you are solving for.